Hello, today we're going to talk about reactivity 3.2.14. This is an HL only topic, and it's all about Gibbs free energy and how we can find that using the cell potentials. So let's review really quick what Gibbs free energy is. We use delta G to represent the change in free energy over the course of a reaction. And typically we're going to be dealing with standard conditions, so 298 Kelvin, 100 kPa, and typically 1 molar concentrations as well. And when delta G is negative, that means there is a release of free energy, which means that it is thermodynamically favorable, which is a long phrase. People will often talk about this as being spontaneous, but many places have moved away from the term spontaneous and non-spontaneous because it has a connotation of being related to speed, but in chemistry it has nothing to do with speed. So Gibbs free energy not related to kinetics. It all has to do with the amount of energy before and after. When Gibbs free energy is positive, it is absorbing free energy. So it is not thermodynamically favorable. And we can also say it's not spontaneous or non-spontaneous. Let me write it like this. So if delta G is positive, it has to have a source of energy to make the reaction happen. So just be careful. You're not talking about it happening fast or slow. It's just whether it is favorable or not favorable under a particular set of conditions. So if we go back to section like 12 and 13 from this unit, we talked about Ecell, and we talked about the cell potential indicating whether the reaction is spontaneous or non-spontaneous. And so Gibbs free energy and the cell potential are related. The equation that relates them is delta G, standard, is equal to negative NFE, standard, Ecell. And this is where delta G is Gibbs free energy, and that's in joules. N is the moles of electrons for the process. F is Faraday's constant, which is 96,500. It looks like an 8, 500. And the unit there is coulombs per mole of electron. And then cell potential, of course, is volts, which is joules per coulomb. I don't know why I wrote it like that. Coulomb per mole of electrons. There we go. So you can see that the units will work out. The moles times Faraday's constant will cancel out moles. And then the coulombs that are left over times the volts will cancel out coulombs, and you'll be left with just joules. So I will say be careful when you're doing this equation, because a lot of times the questions will want delta G to be in kilojoules, but this equation will give joules. So just make sure you divide by 1,000 to get to kilojoules. And then for like moles of electron, you need to be careful with it's how many electrons are present in the overall balanced equation. So if I have something like, let's do that redox reaction. There we go. So we have potentially a molten ionic compound like this, with the ions are separated, and you're transferring the electrons. Calcium is gaining electrons, and the chlorine is losing the electrons over the course of this reaction. So the total number of electrons that are transferred in this reaction is 2. So 2 moles of electrons transferred for every 1 reaction, because the 2 extra electrons from chlorine are being transferred to the calcium. So if I were to solve it for this reaction, I would plug in 2 for N. times Faraday's constant and times the standard cell potential for this reaction. Okay, so let's do an example. Calculate the standard Gibbs energy change at 298 Kelvin for the zinc copper voltaic cell, which has a standard cell potential of positive 1.10 volts. So we know that zinc and then copper the zinc is a negative 0.76 on your, if you use your data booklet, section 19, you can find the standard reduction potentials for these things. So in order for this to be a voltaic cell, it needs to be a spontaneous reaction. So I would go ahead and flip the zinc reaction and flip the sign. So now we have our oxidation potential instead of reduction potential, and then you can add them together. So the zinc plus the copper ions goes to zinc ions plus solid copper, and there's the positive 1.10 volts. You didn't need to do that part to be able to answer the question per se, but I like to show it so you can see what's going on. You do need to know that it's a 2-electron process though. So then you will use our equation delta G equals negative NFE. So this is a 2-electron process. Faraday's constant is 96,500, and our cell potential is 1.10 volts. And so when you multiply those together, you get that delta G is negative 212,300 joules. And if I put that in kilojoules, that would be negative 212.3 kilojoules. And this makes sense because our Ecell is positive. It is a spontaneous reaction or a thermodynamically favorable reaction. So delta G is negative. And here's one more example. If aluminum displaces chromium ions from an aqueous solution following that equation, then the standard electrode potential for that reaction is positive 0.92 volts. So a voltaic cell again. Determine the standard Gibbs energy change for this reaction. So negative NFE, this is a 3-electron process because you're going from +3 to 0 for chromium, 0 to +3 for aluminum, so 3-electron process here. Faraday's constant is 96,500, and our cell potential is positive 0.92 volts. Solve for delta G, we get a negative 266,340 joules, or if I put that in kilojoules, negative 266.3 kilojoules. And so that's how you solve that. Thermodynamically favorable or spontaneous, and a release of free energy for that process. So Gibbs free energy is originally covered in reactivity 1.4 with thermodynamic data, and the main equation that you're going to see for that is delta G equals delta H minus T delta S. So you can use delta H, which is your enthalpy, and delta S, which is your change in entropy, and your temperature in Kelvin, to determine delta G. And if delta G is negative, that is spontaneous or thermodynamically favorable. And if it's positive, when you do that, it is non-spontaneous or not thermodynamically favorable. So you can use these other thermodynamic data instead of cell potential to calculate your Gibbs free energy. So there's just two different ways to wind up with the same concept of how thermodynamically favorable or unfavorable it is.